Hi everyone, welcome to the Python programming series part 15. I am Ram Prasad Pujari. In this video and next few videos we'll talk about linear regression in detail. I will give you complete theoretical and practical information about linear regression. These three videos, which are somewhere connected to today's video, when you get time you can watch these videos. In part 8 I have introduced machine learning and the type of algorithm that you were supposed to choose, so that we discussed. And in part 11 I introduced you to linear regression. We spoke about the coefficients, intercept, etc. And there we have also seen splitting the data set into training and test data set, why it is required, what is the ratio. We also discussed about learning function or the hypothesis function. Briefly, I introduced you to a fit function which is responsible for training. In part 12, we discussed about evaluation metrics or the performance metrics used for evaluation, mainly for regression. And we discussed about three of them: MSE, mean square error, mean average error, and R2 score. And we have seen the theoretical aspect of it as well as the practical demonstration also I have given. So you can watch these three videos and that will be very useful, and you can understand today's video better if you watch these three. So let us look at this particular slide. I have shown a sample of a house price data set. So house price is a continuous variable, area is also continuous in square feet, price may be in US dollars. Bedroom is a categorical value, and then you have a furnishing status, which again is a categorical, which can take three different values. Of course, this need to be converted into numerical value before we start training the model. So label encoder is used here for converting non-numeric label, non-numeric feature into a numeric feature. So this particular data set is a labeled data because we are given the target variable or the output variable along with the features. Now, what type of algorithm to be used if you want to predict house price when these features are given? So we look at the price here, which is a continuous value. So therefore we can go for regression algorithm, and the supervised algorithm need to be used here because we are having a labeled data where x, which are features, y, which is a target variable. So x and y are given to us. So predicting the house price is the problem for a machine learning model. So regression algorithm can be used here. Now the question is, there are a number of regression algorithms called linear regression, decision tree, random forest, etc. So when to use what regression algorithm? So we have to understand this, when linear regression algorithm can be used and when it cannot be used. So this is what we want to understand. This video is more specific to training a linear regression algorithm. Now before that we need to understand what is that factor which decides whether linear regression algorithm can be used or not. So that we want to understand. So when do you choose linear regression? So if you look at this, linear regression assumes a linear relationship between independent and dependent variable. Independent variable is nothing but a feature. Dependent variable is the target variable or the output variable. So let us look at the sample data set which is given here. You have only one feature, which is x, living area or a house area. Then price, house price, which is nothing but a target variable, or y. So let me plot the graph x and y. X axis is house area, y axis is price, and I can see that x and y have a linear relationship in this case. So in this case I can go for linear regression. So that is the condition. If x and y, the features and the target variable, have linear relationship, I can go for it. Of course, even other better regression algorithms are there, but linear regression is the simplest algorithm, minimal number of parameters, easy to train. So but if linear regression can be used, then better to go for this algorithm itself rather than going for a complex algorithm. But this algorithm will work well with a small data set given, like with thousands of samples, etc., training samples. Now here I have just shown 5 training samples, x and y, which is a labeled data set. When number of features are less, then you can go for linear regression. So otherwise you can go for some other regression algorithms. And if you look at this particular graph, and you can see that these are the various data points captured from the data set, and we can fit a line like this by a training process or a fitting process. So we'll try to understand how this fitting process works, how this training process works. When linear regression cannot be used, if a data distribution is complex, let us look at this particular data graph, data distribution, and you can see that it is not linear. Maybe up to certain point it is linear, but after that it is non-linear. In such cases you cannot use linear regression because there is no linear relationship between a feature, that is x-axis, and a y-axis here. Now this particular graph corresponding to the relationship between the spending for advertising media and the sales. So it may not be always linear, maybe up to a certain point it may be linear, but after that there may be other factors which will affect the sales, and it may take a non-linear characteristics. In such cases linear regression cannot be used. So let us look at simple linear regression. In simple linear regression we have only one feature or one x value. So let us take this example of house price data set. So there is living area or a house area, which is our feature, you can call it as x, and similarly house price, which is y, and they are shown here. X and y values are shown, and there are 5 training samples in this case. So now if you look at this particular data set, and if you plot the data points x versus y, and you can see that it's almost linear. So we can fit a straight line here which captures the underlying data, and the straight line function which is given here, which is also called as a learning function. So this is the learning function which we have studied in maths. Y equal to b naught plus b1x. Normally we write it as y equal to mx plus c, where m is the slope which determines the slope, and mx plus c, so c is the intercept, or so that actually changes the origin. Now similar to that, so this is the learning function. So b naught is called as the intercept, and b1 is the coefficient that we have. So b1 decides the slope and b naught decides the initial point or origin, whatever. So this is the learning function, and b naught and b1 are the parameters which are to be estimated, x and y which are given here. So b naught and b1 are to be estimated. So we need to get optimal values for b naught and b1. So if you take a simple linear regression, something like this with only one feature, then there are 2 parameters. One of them is a coefficient, which is b1 in this case, which is also called as a weight because this is a weighing function for x, and b naught, which is an intercept, it is also called as a bias. So there will be always if number of features are p, then p plus 1 parameters will be there, or p plus 1, there will be p coefficients and there will be 1 intercept. Learning function is also called as a hypothesis function. So let us look at multilinear regression. In the case of multilinear regression, there will be more than one feature. As you can see here, there are two features. So there is x1 and x2. x1 is nothing but the house area or the living area, and x2 is a bedroom, which is a categorical feature in this case, and the corresponding y value. So here the x value will be a vector with two elements, x1 and x2, and y value, which is a single valued. So the learning function for this will be something like this. So y cap, let us say, if that is the label, that is the target variable that you have. In that case, b0 plus b1 x1 plus b2 x2. b0 is an intercept, or you can also call it as bias. b1 and b2 are the coefficients or the weights. Now number of coefficients depends on number of features. There are two features, x1 and x2, so there will be two coefficients in this case, plus there is an intercept. So put together there will be three parameters. So number of parameters will be equal to number of features plus 1. So this is about multilinear regression or multiple linear regression. So let us look at machine learning workflow. Machine learning workflow has number of stages, and the very first stage is understanding the problem. You need to define the problem that we are trying to solve. If it is a house price prediction, so that's going to be the problem. And then once this problem is defined, you need to collect the data. You need a data set, and then once the data set is collected, and after that you need to perform pre-processing. The raw data set cannot be used for training. You need to perform pre-processing on this data. And when I meant pre-processing, maybe cleaning the data set may have some null values or missing values, and you will have to handle them. So that is called as pre-processing. We also split the data set into training and test data set. In part 11, I discussed about splitting the data set, how you split the data set into training and test data set. Only the training data set part will be used during training process. Now once pre-processing is done, there is another stage called as feature engineering. The feature engineering where, if there are irrelevant features, if there are redundant features, you can ignore them, and sometimes two features can be combined and a new feature can be created out of it. So this comes under feature engineering. We also normalize the data using scaling operations so that all the features with continuous values will have the same range. Of course, some features will have categorical values, and you cannot normalize them. But if there are, let us say, two features, and these two features have continuous values, and but the ranges are different, so you can scale them so that both of them will have the same minimum and maximum value, let us say between 0 and 1. We discussed about scaling operation in part 10, and you can watch part 10 and part 11. Now once this data analysis is done, we call it as exploratory data analysis. So now we have to select the model. So data set is ready now, so you need to select the appropriate model. Now if it is house price prediction where x and y have linear relationship, then I can go for linear regression model. So that means I define my learning function, which we saw in the previous slide. So we select the model. Once the model is selected, once you have the training data set, after that you can start training a model. So what do you mean by training a model? Training a model is estimating the unknown parameters. We need to get optimal values for b0, b1, etc. So that is those are estimated during model training process. Now During training, you will use an optimization algorithm. There are a number of optimization algorithms which can be used in this case, like OLS, ordinary least square method, or you can also use gradient descent. So we'll discuss about these optimization algorithms later, and the error functions will be used here, and we will discuss this error function in detail in a separate session. So but what we understand here is, during training process, it's also called as a fitting process, we estimate those parameters in the learning function. So once these parameters are estimated, now you have B0, B1 optimum values for them. After that, you can evaluate your model on a new data set, that is test data set. And for evaluating the performance of the model, you need a performance metrics, and we discussed 3 performance metrics for regression in part 12, which are nothing but mean square error, mean average error, and R2 score. So you can watch this video where I explained these 3 performance metrics. So they are used for model evaluation. Once the performance you evaluated, and if you found that the error is minimum, and even during training if it performs very well, in that case you can perform prediction on a new data set, and finally you can deploy it into action or deploy it into operation. So these are the various stages of machine learning workflow. In this session, we'll just focus on step 5, which is model training. Now in order to train linear regression model, there are 3 important scikit-learn statements. The first statement is importing linear regression class from sklearn.linearModel module. As you know that sklearn is a machine learning library. It has got number of modules, and each module will have set of functions. Linear model is one of the modules under sklearn library, and under linear module you have linear regression class, and you can import this. That is the first thing. Once you import linear regression class, the next thing is you need to initialize this object before you start using it, or before you start calling this linear regression model, you need to initialize. So you also call it creating linear regression instance. So in this case, I call linear regression class or object as model. I have named it as model. So that is a statement 2. So once you create this particular instance, and after that you can start training a model on the data set. Statement 3 is used for training a model, and we use a fit function in this case. So model.fit, and then you will have to give the training data. Already we split the original data set into 2 different data sets, training data set and the test data set. Now for training we use training data set. We already have the x value and y value for the training data set. So this will be the input arguments in this case, and fit function of sklearn, which uses ordinary least square optimization algorithm. We'll discuss about optimization algorithms separately in another session, not today. So once this fit function is called, and you will get the coefficients and intercept, you will get the optimum value for the coefficients and intercept. In part 11 I have shown how these coefficients and intercepts are computed. You can watch that video also. So thank you so much.